All right, next example. Cistern for storing water will be constructed. It is the shape of right circular cylinder. With radius r and height h. All right. Must be able to hold 1,000 meters of water, so volume would be 1,000 pi r squared h. All right. The fact that you're given a numeric value for this geometric object means that this is going to be your constraint. Right. Remember, constraint is used to eliminate a variable. It tells you how to find a relevant domain. Right. Now let's talk about what we're maximizing. Right. What dimensions will minimize the cost of materials? So we're minimizing cost. Right. So cost would be $8 per square meter for the sides. The sides here is the lateral surface area to pi RH. And then 10 meters for the bottom, $10 per square meter of the bottom. The bottom of a cylinder is a circle, so that would be area pi r squared. Right, so lateral surface area of cylinder is 2 pi RH. The bottom is pi r squared, which is a circle, and then the top is pi r squared, which we do not use here. All right, so this is what I am minimizing. So what I'm going to do is I'm going to solve for one of those variables. I'm going to solve for h. Which goes in right there. All right, so we get 16 pi r plus 10 pi r squared. All right, so that gives me my cost function. All right, and then let's simplify this. This is 16,000. Pi cancels, r cancels, giving me a -1 power. Come here. All right, so there is my function in terms of one variable, which is the first thing I'm looking for. Next thing is we look at a relevant domain. All right, the variable we're using is radius. So radius is at least 0. And if we set this equal to 0, right, set the other variable equal to 0. Right, if you multiply both sides by pi r squared, you get 1,000 equal to 0. All right, so when you get this nonsense equation, that means that your domain is unbounded. My domain is 0 to infinity. All right, that's the second thing I'm looking for. So relevant domain. Next, I'm ready to take a derivative. -16,000 r to the -2 plus 20 pi r. All right. So in this case, what I'm going to do is, I'm missing something. No, I'm not missing something. Okay. All right. What I'm going to do is I'm going to pull out the highest power of r, or lowest power of r, which in this case is -2. All right. So if I pull out a -2, what's happening is I'm going to subtract. So 1 minus -2. It's going to be a +3. Right, so this is my first derivative. Right, so we get r squared in the denominator. Okay, so what I'm going to do now is I'm going to set the numerator equal to 0. I'm going to shrink this down a little bit so I can have some space. All right, so if I set the numerator equal to 0, oops. All right, let's move the 16,000. All right, now divide by 20. I'm going to get an 800. Then divide both sides by 800 by pi. Right. So my critical point in this case is that cube root of 800 over pi, which is the next thing I'm looking for. Right. Is that we have a critical point. So now we're going to check that we have a min this time. Sorry, min, not a max. All right. So in this case, what I'm going to do is I'm going to take the second derivative because my first derivative wasn't too bad. Right. So using the second derivative test, oh, sorry. Yeah, this is my first derivative. C double prime in this case is a negative 16,000 times -2, so 32 r to the -3, and then plus 20 pi. So 32,000 over r cubed plus 20 pi. But what's going to happen is if I plug in a positive number into this equation, I'm going to end up with a positive value, right? If I cube something positive, right, all the terms are positive and I'm plugging a positive number in. So that means that we are concave up on that function, which means that we have not a max, not a but a min, which is what I want. Right. So now by the second derivative test, we are guaranteed that we have a minimum. And so finally we answered a question, right? What is the dimensions? Right. So this is R, this critical point that we just found. Cube root of 800 over pi. Right. So and then to get H, it's 1,000 divided by pi times this. Right, this is a cube root, and then I'm going to square it. So this is going to be a 2/3 power. And that was the height in this case. In terms of units, it is meters. All right, so that first or the second sentence gives me my constraint. And then the rest of it tells me that I'm minimizing cost. So from there, using geometry, take your cost in terms of one variable, pick your relevant domain, find your critical point. In this case, I did the second derivative test, and then I answered my question, which was find the dimensions.